class for a week, and we had tests before that. So what are we talking about right now? Force types, that's right. And I guess actually I would say we're talking about specifically contact force types. So that's why gravity wasn't in this list. Gravity isn't a contact force, it's a field force. It creates a force field, a way less exciting one than the kinds they show in Super Friends. Right, those are field forces. Yep. So a field force is anything where if you're given the location of the object, you can figure out what the force is. Gravity is that way. In fact, the way we've talked about it so far, you don't even have to know the location of the object. You know the force. It's just the mass times 9.81 down. But the contact force types are, someone give me one. First person who gives me one gets the easiest one. Good job. Pushing and pulling. Spraying? Oh, okay, yeah. Spraying is a subtype of pushing forces. Like the hose. And friction. Yeah. Oh, well, I just heard it for the first time. And that's all, right? That's all. Should be all. Okay. And we're done with this, and so we have these last two to deal with. Thank you. Yeah. Shut up. Oh, well, that's not good, because I want your favorite part to be when you remind yourself to shut up on your own. Okay, so let's first talk about friction. There are two kinds of friction, and you have to treat them differently mathematically. One is called static friction. And that is when an object's at rest. So for an object at rest, this is the friction force that's required to keep it at rest. So let me show an example of that. So the normal force is perpendicular to the surface. We talked about that. That's a pushing force. The friction force is parallel to the surface. And so right now, what friction force parallel to the surface is required for this not to, accelerate one way or the other? There's none, because there's no horizontal force required because there's no other horizontal force on it that it has to balance out. But if I apply a little force like this to the side, now in order for this not to accelerate that way, because I am applying a force towards the wall, that says that if that's the only horizontal force, it would accelerate that way. And so some friction force is required to keep it from accelerating. Okay, and you can imagine if this was frictionless, if I applied this small force to like an air hockey puck on an air hockey table, it would accelerate, you know. The only reason it's not is because there's like a rubber surface between this and the table that can apply an equal and opposite force back and make it not accelerate. That's static friction. It keeps it at rest. And the other type is called kinetic friction. And that's the friction force applied to an object that's already sliding. Okay, so for both of these, an object that's in contact with a surface can have, you know, in general, it has two directions of force applied by the surface. We know that there's a force perpendicular to the surface. That's the one that we've already talked about. That's the normal force. And then the surface can also apply a force parallel to the surface. And that's the friction force. And so if a problem ever asks you what's the total contact force applied to an object by the surface, that's the sum of the force vector, the normal force vector, and the friction force vector. Those make up the contact force. All right, so let's talk about static friction first. So when two objects in contact, normally these two objects in problems are going to be like a block or something resting on a surface, and those are the two contacts, the surface and the, not in contact, in contact. Are not sliding relative to each other. Then static friction is the force required so they don't start sliding. So the force of friction is whatever is required for the acceleration to be 0. Let's see. What? Static so far, yeah. Up to a maximum of force of friction equal to this Greek letter mu times the normal force. You can remember that's mu because it looks like a cross between an M and a U, and that's how you know mu. Yeah, you'll never forget that one. That is the normal force. That you will forget. And this mu, let's put a subscript S under the mu. This is called the coefficient of static friction. This N is the normal force. Okay, so let's think about how these things work. So remember this, we can't calculate, like right now, to keep this thing from accelerating, there's a static friction force pushing in the opposite direction my finger's pushing. Okay? We can't calculate what that is using this formula because this formula only gives us the maximum. Okay. But let's think about how that maximum works. So when, so if I push too hard, this starts to accelerate, right? If I push too hard, it moves and then it's not static anymore. So right at the point where it switches over from staying at rest, you know, where I apply a big enough force to make it switch from being at rest to accelerating, that at that instant, the force of friction is equal to the coefficient of friction times the normal force.
If that's not even like 0.001 tilt, right?
Yeah.
And there's no friction, it's still slide off the table, right? That would be the other one.
Right. Right. But in this case, that's perpendicular to the force I'm applying, so those don't affect each other directly. Right. Yes. In this case, it is, but the way you would do it is you write out Newton's second law. You know that the normal force is a pushing force, so you know the normal force is pushing up. In this case, there's no vertical acceleration. And so add up all the vertical forces. There's a weight force going down. There's a normal force going up. Those are the only two, so those have to balance. And so in this case, yeah, the weight is equal to the normal force. Yeah. But if I do this, you know, if I put a bunch of my weight on it, then there's a third, yeah. So say I push down with 200 newtons, then going down there's the weight force and 200 newtons. Going up is the normal, and then the normal is equal to the weight plus 200 newtons. Okay, so right before this starts to move is that crossover point where you have the friction force exactly equal to this coefficient times the normal. So I just want to talk about what that coefficient is and what the normal. Yep.
So the friction force, that's like parallel to the surface,
right?
Correct? And the normal force is perpendicular.
Right.
So how does a coefficient times a perpendicular force give us?
Yeah. Okay. So I'm going to try to give you sort of intuition about that right now. Okay. So yes. So why is it that friction force depends on the normal force? You know, does that make intuitive sense? And it does if you think about, so right now I can get this to move. You know, I can find that maximum static friction force by pushing this hard, okay? Now imagine that we put a platform on top of this and put an elephant on top of the platform, okay? Do you think applying that same force with my finger would make it start to move just intuitively? No. And the reason is that just in that same way, that 200 Newton force I was talking about, the elephant puts this gigantic force down, meaning the normal force has to get really big to counteract that. So we have this huge normal force, and when we multiply this coefficient of friction times that huge normal force, we now have a huge maximum friction force that can be applied between these two things before it accelerates.
So is that the magnitude of the normal vector and the magnitude?
Yeah.
Oh, okay.
That's right.
So it's like.
Okay, yes. So if I write,
Because you didn't have the vector notes.
yeah, if there's no vector symbol, then we're just talking about magnitudes. Did someone have a question? Yeah.
What if you set it on something like Jello, like then the normal force would be pressing up
Right.
So how
Yeah.
do you calculate that? You have to like find the
Well, it depends what you know. If you know if you can measure the acceleration down through the Jello, then
measure the mushiness of the Jello.
but if you could measure the acceleration, then you can just calculate the forces. If yeah, right. Okay, so wait, I'm not done with this. So we talked about how the normal force affects it and why this maximum friction force is proportional to the normal force. Now let's say we take, well, let me put this on this. So now I've changed the surface of contact between these, and there's sort of a smaller kind of stickiness between the paper and the desk than there was between the rubber and the desk, okay? So now if I apply the same, like if I apply a force where it stayed at rest before, now with the paper under it, it'll start to move, okay? And that's what the coefficient of friction does. It tells you what's the stickiness between those surfaces. Between rubber and whatever this surface is, that's a relatively high coefficient of friction. There's a stickiness. Between paper and this, there's less. And so, like, you can go online and Google coefficient of static friction for, metal versus wood, or, two wood pieces, or something on ice at a certain temperature, stuff like that. It's just a measure of how sticky the two materials are to each other. And so you just multiply those two things together to figure out what's the maximum force of friction you can apply. Yep. So yeah, that's a good question. If the shape is anything but two smooth surfaces sliding over each other, then that's not really friction that's causing them to stick, So then you have to deal with the geometry of it. So, like, for example, if you had something that had like two jagged edges, and you say, well, and they can sort of lock in place, and then you think like, oh, well, that's way more friction than the equation says, but it's not really the surfaces. Yeah. One other thing that is sort of surprising about this is notice that this equation doesn't say anything about the surface areas in contact. So you would think so, and it does it does make a difference, but not as big a difference as you might think. And so we're going to assume that it doesn't make a difference at all. So what that's saying is, if I had, so this thing with its small surface area, if I spread that out over something with the exact same weight, but 50 times the surface area, supposedly that maximum force of friction stays the same. It doesn't exactly, but it's a fairly good approximation. Same weight, yes, right. Okay, so let me do an example for static friction. So let's say that this box is 10 kilograms. There's a 40 Newton force that way, a 20 Newton force that way. Let's say that the coefficient of static friction is 0.4 between these two surfaces. I didn't talk about units and stuff. Look at that expression for the force of friction and tell me what the units are of the coefficient of static friction. Well, the units of the normal force are newtons. The units of the force of friction are newtons. So what do you have to multiply to newtons to get newtons? Scalar, just a pure number, yeah. So this doesn't have any units. So we'll just write this as, 0.4. It's like a fraction. And that coefficient of friction is almost always less than 1, but it doesn't have to be. There are some combinations of surfaces where the coefficient is bigger than 1, but it's not very common. Rubber on cement or something is, you get more stickiness horizontally by applying a downward force than you do by applying that same force. Like, if you're trying to keep a tire from sliding out of your truck, you know that you're capable of applying with a tether or something 1,000 newtons of force to it, you get more bang for your buck applying that force straight down on it to create more friction than you do using it horizontally to hold it in place. And that's because the coefficient of friction is more than 1. What? No matter what heavy. If it's too heavy, then that's not going to be enough. Yeah, I don't know. I just made up 1,000 newtons. Okay, and the question is, this is initially at rest. Does the box start to slide? Can anyone think of what a sensible approach would be for this? This is really something you could just kind of think through. Yeah. Well, 10 kilograms times 9.81, so that's 98.1 newtons. But so the way, like as a sort of systematic way to think through it, we're just going to draw a free body diagram, find the normal force, plug that in. We're going to assume that this thing is at rest. We're going to use Newton's second law to figure out what that friction force has to be to keep it at rest. And then we're going to compare that to the maximum friction force. Okay, so free body diagram. We have 40 newtons this way. 20 newtons down, a weight of 98.1. Then the contact force is a normal force and a friction force that we can see the only other horizontal force is to the right, so this friction force has to be to the left. And this has, we'll just call this FF. Okay. And now we're asking, what's the FF for the acceleration to be equal to 0? So Newton's second law says 40, 0 plus 0, negative 20 plus 0, negative 98.1 plus, it's pointing down in the negative y direction. The normal force is N in the positive y direction. And the friction force, the way I have it drawn there, is in the negative x direction. And if it stays at rest, the acceleration is 0. Yeah, so the thought process here is we want to know whether it moves or not. And it's going to move if the static friction force that we're requiring to stay at 0 acceleration is bigger than the maximum. Like if it would take more for it to stay at rest than the friction can provide, then we know it moves. Yeah. So that's the thought process here. We're going to assume it stays at rest. We're going to figure out what FF would have to be for it to stay at rest, and then compare it to that maximum value. It's 10 kilograms, so the force is 98.1. Okay, so the x equation says 40 minus FF is equal to 0. So that force of friction is equal to 40 newtons. This is the force that would be required to stay at rest. The maximum force of friction is equal to the coefficient times the normal. The coefficient is 0.4. The normal from the equation above, we can calculate that from the y equation. So negative 118.1 plus n is equal to 0. So n is equal to 118.1. So plug that in here, you get point. Yep, that's right. Yeah, I mean, not in every problem, but every problem has to give you that, or give you enough other stuff to solve for it. No, right. So between rubber and cement, it'll be 2.3. Between two pieces of the same kind of wood, it'll be 0.1 or something. That's so. Yeah, so that's already been calculated for every combination of materials you could want. So for us, we just go to Google and look it up. But to calculate it, you put two of these smooth surface things together, and you calculate the force that it requires to get it moving, and then you use that and then you use the equation the way you were saying, solve for mu. Yep. Nope.
Yeah, that'd be
That's right. That would be awesome. If you could ever get friction to make things speed up, that. Uh huh. Okay, so now we have to figure out. Now we want to compare. Could someone multiply that? Do I have that? Oh, I do. Okay. 47.24 newtons. So now we're going to compare to this maximum. So we got that in order for this object to stay at rest with the forces on it that we know are applied, it took 40 newtons. We know that the coefficient times the normal, the maximum static friction that can be applied in this case is 47.24. So does this stay at rest, or? This stays at rest because basically the friction can cover that force. That force isn't a problem for it to apply. If the required force of friction got up to, 48, then at that point the thing would start to move. So since the force of friction was less than the force of friction max, this object stays at rest. Let's do one more. Okay, so let's say we have this 5 kilogram mass on a surface connected by a cable and a pulley to a 3 kilogram mass. The coefficient of static friction is 0.5. Does the box start to move? So we're going to assume that it's at rest, the same as we did in the last one. We'll do a free body diagram of the 3 kilogram. There's a weight acting down of 29.43. That way? Or towards the blank page? I just want to look at a blank screen for a minute. Okay, so now Newton's second law. So Newton's second law for this one, we only have those two forces. There's cable force in the positive y direction, the weight force in the negative y direction. And what am I going to put here for mass times acceleration? 0, because for these static friction problems, we're always assuming the thing's at rest and then seeing if, yeah, we started this several minutes ago. Okay, so 3 times the acceleration of 0 is 0. And so from this, we can calculate the cable tension. So T is equal to 29.43. That one didn't have anything to do with calculating the friction, but it just let us calculate the T that we're going to need when we isolate the box with the friction on it. Okay, let's see if you can work through this one. Just we don't have to do it on the board. Just see if you can. Now you're going to ice. This should just not say that. Yeah, do it on the board if you want to. So now you're going to do a free body diagram of the 5 kilogram box and see if you can get through and calculate whether this moves or not. That's true. Da 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 da. Guy, time. Okay, so as Colden would tell you, start with the free body diagram. So 49.05 down is the weight. There's a normal force N. There is the tension force that we calculated from before, so this is 29.43. And to keep it from moving, we need a force going this way. That's our force of friction. And that's everything. So Newton's second law says negative FF0 plus 0, negative 49.05 plus 0, positive N plus 29.430, and that's equal to the mass times, we're assuming it's at rest, so 0 acceleration. The y equation says N is equal to 49.05. The x equation says the force of friction is 29.43. So that's what's required for this to stay at rest. So now we have to calculate F max. So the maximum force of friction is the coefficient times the normal force. And that is, what do we say, 0.5? 0.5 times the normal force of 49.05. And that gives you 24.525. So now we're comparing this, what's required for this to stay at rest, to this, which is the maximum friction force that this system can muster. So this will move because the force of friction required is greater than the force of friction max. Any questions about that? Okay, so that's static friction. That's a little more complicated than the next one. The next one is a little simpler. So kinetic friction. So with static friction, how many possibilities are there for the friction force that's applied? Like 1 or 6 or 4? Well, so it can be anything. It's, there's a continuous range of possible friction forces that can be achieved. Like here, there's none.
Now there's a little more, now there's a little more, anywhere in between, right? So you don't know what the value of the friction is from that coefficient times normal thing. You only use that to figure out if what is required is attainable by the friction. In kinetic friction, it's different. If the thing is moving, you just always straight calculate what the friction force is. So the friction force is always the same if the object's moving. The force of friction is the coefficient of kinetic friction times the normal force, and the direction is opposite the direction of the velocity, opposite the direction of motion. You don't have to worry about a maximum and if, you know, what you have is possible and all that. You just do that calculation and you're done. Yeah, that's better. By the way, this is kind of an interesting thing. Notice the coefficient of static friction is always greater than the coefficient of kinetic friction for any two surfaces in contact. Did you know that? Now you do. So you can apply a bigger force of friction in static friction than you can in kinetic friction. And you had that experience probably from trying to slide like a heavy box full of stuff across like a wood floor or something. You know that once you get it started, you want to keep it moving, because if you have to get it moving again, you're going to have to apply a bigger force to, you know, that bigger force is the static friction that you're overcoming, and it's always more force than the kinetic friction. And the reason for that is like the little microscopic entanglements, like when something comes to rest, they sort of get into the gaps and they just can hang on tighter than if you keep the things moving. They don't have time to grab, you know. Which, by the way, is why anti-lock brakes are a thing. Because when an object's rolling without slipping, you're in static friction instead of in kinetic friction. And so the friction force that you can get, that's what you're using to stop yourself, is bigger if you remain in static friction than if your wheel breaks free and now it's sliding. Now the friction force you can apply goes way down. Anti-lock brakes. This is why. Yeah. Okay, so I'm just going to do an example. You approach these always the same way. So let's say we have a surface and a 10 kilogram object, and you apply a 30 Newton force this way. Let's say that the coefficient of kinetic friction is 0.1. So first, what's the force of friction if the box is sliding to the left? And second, what's the force of friction if it's sliding to the right? Okay, by the way, what kinematic quantity would tell you what direction it's moving? Velocity, yeah. So the friction force always acts opposite the velocity vector.
And this is the first time in any of our kinetics problems that we've had to know anything about velocity. But you can't do kinetic friction without knowing what the velocity direction is. So in all the other problems we've done, what's the velocity been for our calculations? So that's a reasonable guess, but the fact is the velocity hasn't mattered at all, and so it could be anything. In every problem we've done up to now, we do the calculation, and it would be true if the thing was moving 50 miles an hour this way, if it was at rest, if it was moving fast this way. But now that's changed. Okay. Yeah, everything. Okay, so what's the first step? Yes, that's right. The system. Trust the system. Yeah. What? Yeah, it's in part B, it's also sliding just the other direction. Okay, so there's a downward force of 98.1. There is a force this way of 30 newtons. And then the contact force, there's a normal force that way. And which way does the friction force point? To the right, opposite the velocity. And this time I'm just going to write it in as the coefficient times the normal. So Newton's second law says negative 30, 0, plus 0, negative 98.1, plus 0n, plus positive 0.1 n, 0, is equal to the mass times, this time it's moving, so there can be acceleration. What do we know about the acceleration? It's only along the x-axis. So we'll just write this in as A0. And you don't have to think about whether it's positive or negative. That'll come out. Okay, so first, these will always go the same way. Use the y equation to find n. And use the x equation then to find the acceleration. So negative 30 plus 0.1 times 98.1. Yeah. That n is for the normal force. So anytime I write the, anytime I draw the n with the things on the fancy flourishes, then that means normal force. So it's 0.1 times, in step 1, we calculated that the normal force is 98.1, and then we plugged it into the x equation. Okay, so 30, negative 30 plus 9.81 is negative 20.19, right? That's equal to 10a. So a is equal to negative 2.019 meters per second squared. But that wasn't really what I asked for. What I asked for was the friction force. And the friction force vector you can get from, you have this value of N. Now just plug that into, here's the force vector. Just plug it in there, and you get that the force of friction is 9.81 in the x direction, 0 in the y direction. Right. I just like to know what it is.
Curious person.
Yeah, exactly. Any other questions? This N is Newton's because it's plane. Yeah. All right. So one thing that we are going to always do so with all sliding and rolling problems, you want to choose a coordinate system where the y-axis points out of the surface and so that means that the x-axis has to be parallel to the surface. Okay, so let me do an example. Let's say we have a block on this incline, 5 kilograms. There's a 50 Newton force. We'll say that there's a static coefficient of friction of 0.4 and a kinetic coefficient of friction of 0.1. So first, we're going to use a coordinate system with y pointing directly out of the surface, and so x has to be this way. So what's the acceleration if at this instant the box is sliding down the block, down the incline? And then second, if the box is at rest at this instant, bless you, does it stay at rest? Okay, so first, for part A, I'll draw a free body diagram. Yeah. Yeah, try to do part A on the whiteboard.
I'm going to draw a free body diagram.
Yes. This is the start of a free body diagram, but I want to see if you guys really trust the system now, or if you still are sort of off on your own. Yeah, I don't know how well any of these work.
That was a little bit extra.
Doesn't work.
Are there more in here?
Here, see if either of those work. Yes. Oh, here, let me throw that. I was trying to get in the garbage. That one's dead. No, thank you. Let's do part A.
What did you drop? What did you drop? What did you drop? Upside down started walking. Oh no! You're right with the gutter. God.
Oh, yeah. We didn't know the angle.
Oh yeah, that might be helpful.
20 degrees.
If our coordinates is like y, x, now we have to find what this vector is. So okay, let's draw this. We got there. This. So it's like magnitude, for example, and oh, which angle is 20?
Why is it going down?
No, we need to be told what direction it's sliding. Because that determines which direction But yeah, you have to be told which direction because the friction force always goes the opposite direction. Yeah, I think you'll be happier if you just draw the whole thing tilted, you know. But that's right.
We were trying to figure out like what that is. Like
Yeah. Yeah, no, that's perfect.
Okay.
But I'm just saying, draw it like that. Draw it like that. So this is 49.05. The angle is 270 plus 20.
Oh, what is it?
In the first case, it's starting. It's already sliding. No, that's only for stats. Right, we know it's sliding down. And we know it's moving forward. Not for parties.
times, okay, so 0.3 times 49.05. No, times 49.05. Okay, and then
You know that the acceleration is only along the x-axis, and so you can still calculate that. The wildlife. Right.
Okay, so that's that. What? Okay, rewind guys.
Clara, here's
That was
something I think was best to do. So everything there is right, except your right force looks like it's parallel to the normal force. The right force is really straight down. So make it clear to yourself on that diagram that those are your measures. And that also points out that you have it drawn too, written too simply in the law because it's in an angle. You know, so now you have to deal with the weight force.
okay, so that one's kinetic. That might help.
Yeah. What is the normal force that's like?
You guys had the normal force right before. The normal force is perpendicular. It's only the weight force.
The normal force is perpendicular.
So, yeah, so you can think of the weight force now as going to be 4 times cosine the sine of
Oh, yeah.
because here. So your coordinate system is
And it's sliding in the x direction. Yeah, but it's in the x. I'm trying. Because our coordinate.
Yeah. Okay. So now we solve.
I read these cards.
It's in the opposite direction of movement.
No, the acceleration or the acceleration.
Calculator.
There's one right here and then we're good.
All we have to know about the path is direction. That's a very
Okay,
Yellow.
negative 5.7296.
Negative 5.7.
Point seven.
Wait, 5.7.
I hope you're right, but
So it means that it's slowing down.
So I just murdered. Yes. The only drawback is it takes 0.
Oh, we have a second part of the problem.
he said just do one.
But it's trying to teach.
Wait,
Because it has a y direction.
I'm kind of I really kind of want to try to see. Like, we're going to choose. There's like all the doors have different levers. That
Why would it be on?
why would we I do two open them. Like I do two open groups and one of them monsters. Not yet.
Nope.
I could do it. I think I will do one sister and one. Tim, this sounds so bad. Why are we picking C?
Okay, everyone sit back down. Let me finish this before you go. Hey, that's right. Good job.
we got our
Yeah.
You did it right.
Yeah.
Doesn't sound very good.
Okay, so free body diagram. You have the weight force straight down. You have a 50 Newton force there, a normal force there. It's sliding down the ramp. That means the friction force is up the ramp. And that has a magnitude of 0.1 times the normal. So Newton's second law says negative 50, 0, plus 0n, plus negative 0.1 n, 0, plus, and now the only one that's sort of a pain to deal with is the weight force now. That's always been the simplest one to deal with, but now you have to think about the angle. So if that's your coordinate system, and this is the weight force, this angle is 20 degrees. Yep. The weight force just always goes straight down, and so if you have a tipped coordinate system, that doesn't affect the direction of the weight force, you know? It just affects how it relates to the coordinate system. And so the angle then is 270 plus another 20, so 290. This is 49.05 cosine of 290. 49.05 sine of 290. And all that's equal to the mass times the acceleration. What do we know about the acceleration? It's parallel to, yeah, we don't know if it's positive or negative, but we know it's parallel to the x-axis. And so the y equation tells us that n is equal to negative 49.05 times the sine of 290. So that comes out to be positive 46.092 newtons. And because we have that negative in addition. And then the x equation says negative 50 minus 0.1 times this, so minus 4.61, let's call it, plus 49.05 cosine of 290 is equal to, we know this mass is 5. And so A is equal to negative 5.72 meters per second squared.
We messed up.
So that it was
We
positive
did positive with one
and
end,
negative.
but if you're saying we came up with the same answer, then that's
Oh, because you got your,
We like did the
we just
we
did
forgot the
positive
negative.
for one instead of negative one end.
that's funny.
But we still came up with the same.
How would it, if it's on a tilt, how would it still be negative 0.1 for the normal? It would be 0.1 times sine or whatever.
Well, we tilted our coordinate system.
So you tilted, oh.
Yeah. So, and the reason we tilted it is because so much of the stuff is simpler if you tilt it. The only thing that gets more complicated is the weight. Everything else makes it faster. Okay, so last question about this is,
Yeah, no, it's negative 7.56.
I have it in my notes. Those are never wrong. The sliding is in the positive x direction.
It's sliding
Yeah,
down.
we messed up there.
No, it says sliding down. Like scroll up, scroll up.
It says, what's A if the box is sliding down? Yeah.
Oh,
Yeah.
So I just,
wait, so how, what would the box sliding down change?
It changes the direction that the friction force acts. So if I said that the box at that instant was sliding up, the friction force would go in the positive x direction. Okay, so in this case, yeah, we just have to know which direction it's moving so we know which way. So yeah, that's the next question I was going to ask. Is it slowing down or speeding up? Slowing down, and you know that because the velocity is in the positive x direction and the acceleration is in the negative x direction. Really?
yeah. I just redid the calculation twice.
That's weird because I got the same thing as you in my notes here, but
You must have done the same
That's funny. 7 point what?
7.566.
Okay. Any other questions about that? All right, that's it. Yeah, good class today, everybody.